All right, so in this video, what we're going to do is take a look at another aspect of the C4v character table. We're going to be looking at the different functions and showing how these different functions transform as these different symmetries. So in a different video, we used some of these functions to help us derive the character table, and that's one way that this all can be done. But here I'm going to go through and show you how the different functions, where they come from in terms of their symmetry, at least most of them, or the important ones, and also walk you through how it works for quadratics and even the cubic functions. Remember, the quadratics have relevance for a lot of different types of spectroscopies, IR spectroscopy, for example, and also it's how the px, py, and pz orbitals transform. The quadratics are useful for Raman spectroscopy and also for how the d orbitals, the 5d orbitals transform. The cubics can be used for the f orbitals. So let's just, for review, we can look at the other video for more details of deriving this character table, but we always want to start with an example molecule. And so for C4v, I've been using iodine pentafluoride. Any sort of square pyramidal type molecule will do just fine. It's sort of the simplest C4v type of molecule you can think of. And so there's the square pyramid, and then there's the apex of the pyramid. And how we define things here is that our z-axis is where our principal rotation axis is. We always have to define the z-axis that way for the character tables to work. That's how the character tables are defined. And our x-axis and our y-axis, we have to have perpendicular to one another, but we can define them in various different ways, and mathematically it'll all work out. So as long as your z-axis is with respect to the principal rotation axis, you'll get the right answer. Okay, so as review from a previous video called Deriving the C4v character table, we're going to go over the linear functions first. So we think about what happens if we have a z vector. And so if we have a z vector, let's say in green here, and we do the identity on anything, well, identity on anything just goes to itself. So the character, since we're going to z, there's a 1-by-1 matrix here. So the character, I always use the symbol chi of the identity transformation is 1. And then if we do the same thing for C4, one of the C4 operations in the C4 class, C4 or C4-3, Z also goes to Z. And so same sort of logic, you're going to get a chi C4 equals 1. Why is Z going to Z here? Well, we're doing a C4, right, here. And we're rotating this vector just like this. But the vector, when we rotate it across the z, well, it is the z vector. We're rotating it for 90 degrees, doing a C4, still pointing up. We're still doing that same sort of direction. So the vector still says, the same thing. So we get a 1. C2 is a 180 degrees that way. It's still in the a z rotation, so it's not going to change the z vector. So again, we're going to get chi C2 equals 1. And we keep going here, and all these end up being 1. Sigma V, any of the sigma V mirror planes, those, for example, one of the sigma V's is like this. The other sigma V is going 90 degrees to this, but they both contain the Z vector. And so if something is in the plane, it doesn't move. And so then Z is going to go to Z. And same thing with the dihedral mirror plane. The dihedral mirror plane, remember in this case, breaks through and bisects in between. It's a little hard to draw here, but it's going in between here. And again, the Z vector contains it. So Z is going to go to Z. And so nothing, at all interesting is happening here. But this is why we have 1s across the board. So it transforms as A1. It's a totally symmetric rotation. So moving forward, we're just going to sort of remember that because Z is very easy to remember, that they all transform together. And so From here, what we can do is, and I'm just going to erase part of this here because we can use a lot of this writing for the x and the y. And so the x and the y for all this are a little bit different. So we ran into an interesting situation here wherein when we did the x, we got x goes to x for identity, but y, of course, is going to go to y. And so that looks all fine. It looks like they're transforming separately. We'll get a 1 for x and 1 for y. But then when we get into the C4, if we think about an x vector here, an x vector rotated 90 degrees. If we rotate this way, we could rotate this way or rotate this way. That would be a C4 3 times. C4 3 and C4 are both in the same class. Let's see the previous video. But if we rotate that, we could say it goes x into y. And so now we get x into y, and y vector, if we have a y vector, let's say in blue here, that is going to transform and go to 90 degrees, which is going to be actually the negative of x. So y is going to go to negative x. And so what we see here is that we can't write a matrix. There's no matrix that takes x, a 1-by-1 matrix that goes into y. That's just an impossible situation. So instead, we need to have a 2-by-2 matrix where x and y are transforming together is the language that we would use. And so we're asking, what is the 2-by-2 matrix that takes x, the matrix, the 2-by-1 matrix, x, y, and converts it into y minus x, because x is going to y and y is going to negative x. And so our answer here is going to be 0, 1, -1, 0. And then we're going to take the trace of this matrix to figure out the character. Remember, that's where the name character table comes from. It's the characters of the matrix, which is the trace in linear algebra speak, which is just a sum across the diagonals. So the trace here is going to be 0 plus 0, and that gets us chi of 0. Well, back up here, when we're doing the identity, we're going to have the so-called identity matrix. And we're going to again have to keep it as a 2-by-2. Since we had to keep it 2-by-2 matrix here, x and y transform together, we got to do the same up here. So we're going to have the same sort of thing, but now our matrix is going to be the identity matrix, ones across the diagonal, that takes xy into xy, and we take the trace of that matrix. 1 plus 1 is 2. And so our character is going to be 2. So you can see how this is lining up. We have a character 2, a character 0. That's what we calculated here. And what we're calculating here is how x and y transform together. They're going to transform as e. We can already see that. That's already the only option here. But let's keep going. To prove this, x is going to spin with C2, 180 degrees, into negative x, and y into negative y. So that's going to get us a 2-by-2 matrix with a negative 1s on the diagonal for negative x to negative y. We take the trace of that, we get negative 1 plus negative 1 is negative 2. So that's matching up here. Moving right along, x goes into what for the sigma v? Well, the sigma v, one of the sigma v's is right here. We can use either of the two sigma v's. X in this, for this sigma v, x is in the mirror plane. The x vector is in the mirror plane. So x goes to x. The y vector is looking at itself in the mirror, and it's going to flip over into negative y. So we end up with a 2-by-2 matrix describing this as 1, 0, 0, negative 1. That's the matrix that makes this into x and negative y. And we take the trace of that, and we get 1 plus negative 1, which is 0. That matches character up there. Last one, x for the dihedral, and I'm going to, for clarity here, just erase some of these vectors here and stuff that we have drawn. But what we have here now is, let's see, that was my iodine. We're going to have a mirror plane, one of the dihedral mirror planes cuts through and it goes at a 45-degree angle versus the x and y's. It's cutting it's not cutting through the bonds, it's going in between the bonds. And so now each of these vectors, the x and y vectors, they're looking at each other in the mirror at 45-degree angles. So x is going to go into y and y is going to go into x. It's sort of a diagonal mirror. Okay. And so the matrix that describes that is 0, 1, 1, 0. One's on the off-diagonal components. That takes x, y into y, x. And when we take the trace of that, we get 0 plus 0 is 0. And we ended up with a 0 there. And we got our 2, 0, negative 2, 0, 0, which is exactly what the E vector is. So we prove that xy transforms as E. So that is all pretty fun. Now that we know that, we can do any of the quadratics or the cubic functions fairly easily. And so I'm just going to go to the next slide here and clear all that and show you how the quadratics would work. So as an example, let's do xy. I think that's a nice, easy one to start out with. So again, we do the same sort of logic. We say, hey, how does this work with the identity? Well, we know previously that, well, x goes to x with identity and y goes to y. So xy just goes to xy. And the character there is going to be equal to 1. That one's not very interesting. You could just say, well, xy is going to stay the same, goes into xy. So we don't really learn much from going over that example, but let's do C4. So the C4 operation, we know that for the x vector, if we recall from what we did previously, x actually went to y and y went to negative x. And so the way that we do this then is, well, x went to y, so we're going to put a y there, and y went to negative x. Well, y times negative x is negative xy. And so the 1 by 1 matrix that describes this, is simply negative 1. Right? Xy times negative 1 equals negative xy. We take the trace of that matrix, well, that's negative 1. So we got chi of C4 equals negative 1. And you can see there's xy, and we're matching so far. We have 1 and negative 1. Our next one should be 1. That's for C2. Let's check it. xy. Well, remember that for C2, x went to negative x. That was a 180-degree rotation. And y went to negative y, another 180-degree rotation. So we got xy going to negative x times negative y. That, of course, is equal to xy. So xy ended up just going to xy. That gets us xy going to itself. And so that gets us a character of equal to 1. Moving right along, if we do sigma v, ask the question, how does xy transform? Well, on sigma v, the example that we used last time earlier was that we used the sigma v that contained the mirror planes, contained the x vector in the mirror planes. X went to x. By the way, there's a plus 1 from before. And y goes to negative y. So we get y going to x times negative y, which equals negative xy. So the character for sigma v operation in the sigma v class is going to be negative 1. And that's what we got here. Our last one should be plus 1. Let's check that. xy, what does it go to? Well, for sigma d, x went to y and y went to x. That's the example we used. So we got xy going to yx, and of course yx is equal to xy, so xy went to y, so nothing changed, so we get a 1. Indeed, that's what we got. So that's all you really have to do here for these quadratics. Let's do one more example here on a quadratic. Let's do, how about x squared minus y squared? So we can keep going here. We're going to do x squared minus y squared. Well, identity is our first one. That's always very boring. X squared minus y squared is going to go to itself. So the character there is going to be a 1. Um, and, we would always get a 1 in the beginning, or what we think is a 1 in the beginning for a function, until later on, perhaps we might see that two functions have to transform together, and then that would get us in this E space, right? But we kind of know the answer already. We're not going to have that here. So let's go to C4. C4, if you remember from before, we said X went to Y and Y went to negative X. So what happens there? X goes to Y, so we're going to get Y squared minus negative X. Y went to negative X squared. Well, that equals Y squared minus X squared, which equals negative X squared minus Y squared. So X squared minus Y squared ended up just going to, sorry, there should be an arrow here, going to, when we do the operation, to a negative of the quantity X squared minus Y squared. So it went to a negative of itself. So that tells us the character must be equal to -1. And indeed, we get a -1 there. So that's sort of the crux of it. That's the interesting part here. We keep going with C2. C2, we know that X goes to negative X and Y went to negative Y. These are the 180-degree rotations. So X squared minus Y squared goes to quantity negative X squared minus quantity negative Y squared, which of course is just equal to X squared minus Y squared. So X squared minus Y squared just went to itself. So the character is going to be a +1, and that checks out. Let's go to the sigma V. Sigma V, we had X going to X and Y going to negative Y. So what is X squared minus Y squared going to do? It's going to go to X squared minus Y, quantity minus Y squared, which equals X squared minus Y squared. So we get sigma V, chi of sigma V, the character of sigma V is equal to 1. Nothing changed. That checks out. And our very last one here, we're running out of room, so I'm just going to erase something. Very last one here is going to be our sigma D operation. Our sigma D operation, if you remember, X went to Y and Y went to X in our example of the sigma D that we chose in our axis system. You always get the same answer if you choose a different axis system, as long as your Z is coincident with the primary rotation axis, and you do all the math right, you'll always get the same answer. It's amazing. This is why the character table works. It's because it just preserves mathematically, it just preserves the key elements of the symmetry. And so it's pretty neat how it all works out. But anyway, X went to Y and Y went to X. So X squared minus Y squared is the question we're asking. That's going to make us go Y squared to minus X squared, which is equal to a negative of X squared minus Y squared. And so X squared minus Y squared went to the negative of itself. So pi of sigma D equals -1, and that's what we see right there. So this is very similar for all these, and the cubic ones in this example aren't super interesting for the most part, because you can see what happens if you multiply by z. Like if you multiply xy times z, you get the same symmetry because z is totally symmetric. And so that makes sense mathematically, right? Or if you square z, you're going to get, well, that was just z squared, it's all the 1 squared. So it's going to equal the same symmetry. Z cubed, same thing. Maybe let's do something that is a little more different. Let's do try to check these functions. So let's say we wanted to first ask, what was xy squared? So if we didn't know this beforehand, we wouldn't know that they transform together. So if we were just, evaluating xy squared, what's the symmetry of that? First, we would start off and we'd say, all right, identity, what does identity do to xy squared? Well, it takes it into xy squared. That's pretty interesting. At this point, we think the character is equal, uninteresting. So at this point, we think the character is equal to 1, we would move right along to the C4, and we know what the C4 does. The C4 takes x to y and y to negative x. We got these all memorized at this point from the previous example, working through this so many times. But this is a 90-degree rotation, right? So what's going to happen to xy squared? Xy squared, well, is going to, x went to y, so that turns into y, and y went to negative x. So negative x squared, that's equal to x squared y. And so here's where you can see, hey, xy squared went into x squared y. That's why these two functions are transforming together. They're linked. Okay, so that means we have to look at x squared y and see what it does. And so back up here, we have to say, well, x squared y goes into x squared y. It's the identity. And we know they're linked, so there we get the identity matrix, right? And so there's no problem there. We're getting 1, 1, 0, 0, and this matrix, sorry. What this matrix is saying how xy squared and x squared y transform. If they transform as the identity matrix. And the trace of the identity matrix is 2. So we get a chi for identity equals 2. And so that's our 2 up here. Now this one better be 0. So let's work through this. So we did xy squared goes to x squared y. What about now x squared y? We know that these transform together. Well, x went into y, so we get y squared, and y went into negative x. So we're going to get times negative x. So this is equal to negative xy squared. So it's the negative of this one. So now we can write our matrix, xy squared, x squared y. This is definitely the most interesting example of the video. And what we end up getting was, well, xy squared went into x squared y. So we're going to have actually a 0 and a 1 here, and then a negative 1 and a 0. And what that matrix is going to get us is x squared y and negative xy squared. Okay? And so now we take the trace of this matrix and we get, lo and behold, we get 0 plus 0, and we get 0 just as we expected. So let's keep going. Our next one, we're hoping to get negative 2 if this checks out. So let's see what happens. So we get xy squared. Xy squared, well, x went, what does x do in C2? X goes to x. X goes to negative x. This was a 180-degree rotation, and y went to negative y. So x is going to go to negative x, and y went to negative y, and it's squared. That equals negative xy squared. So it went to a negative of itself. That's looking good. And then what about x squared y? X squared y, this is the other component of the function that's transforming together. Well, x went to negative x, so negative x squared, and y went to negative y. So we end up with, again, negative of itself, negative x squared y. And so we write our 2 by 2 matrix for xy squared and x squared y, and we get the inversion matrix, negative 1's on the diagonal, because that takes it to negative xy squared and negative x squared y. We take the trace, the character of the matrix, the sum along the diagonals. We get negative 1 plus negative 1. And nice, we get negative 2. Okay, so we've checked those 3, and it's looking good. And so our last one, remember we're doing these functions here, we're doing x y squared and x squared y. And so our last one, or second to last one here is for sigma v. A sigma v, if we recall, x went to x and y went to negative y. We had this mirror plane in the x plane, containing the x vector, and the y vector was looking at itself in the mirror plane. So it went into negative of itself. And so we're asking now, what does xy squared do? Well, x went to x, so that gives x, and y went to negative y. That's squared, so it ends up just going to itself. And now we ask the question for x squared y, what happens? Well, x went to x, and y went to negative y, and so that is going to the negative of itself. So our matrix of xy squared and x squared y, how does that transform? Our 2 by 2 matrix is 1, 0, 0, negative 1, because that gives us xy squared going against itself and x squared y going to a negative of itself. And so now we take the sum across the diagonal, and lo and behold, we get 0, which is what we wanted. Last one here of the video, and we're done checking, is just sigma d. So we should get a 0, and let's see if that holds. So sigma d, if we recall the example that we used of the mirror plane we used, there's 2 different sigma d's, you can use either. But with the axis system that we had, x went to y and y went to x. So now x squared y, x went to y and y went to x. So we're actually going to get yx squared, which is the same as what we've been writing, x squared y. All right, and then our other one is xy squared. We ask, x squared y, and we ask how that transforms. Well, x went to y, so it's going to go y squared x, which is equal to xy squared. So what we can see here is that they crisscrossed. The 2 functions went into each other. So our matrix is going to look like off diagonals. One's on the off diagonals. It's going to look like this, where xy squared went into x squared y, and x squared y went into xy squared. And so now we can take the sum across the diagonal and get 0, and that exactly is what we got here. So, chi of sigma d operation is equal to 0. So we show here. So that's just one example of the cubic functions. All these other ones would work out very similarly. These are relevant for F orbitals. And hopefully now you can see how you can derive any of these. The only one that we didn't do in this video was the rotation vectors. I showed how to do RZ in a previous video when we derived the C4v character table. What RZ is it's a rotation vector that's wrapping across the z-axis, so the principal rotation axis, that C4 axis. And basically what you do is you look at if this changes direction. So this vector, you can define it as counterclockwise or clockwise to begin with. And then if an operation flips it to be counterclockwise, then you know that you have a -1. It's anti-symmetric. In the case of Rx and Ry, it's very similar to X and Y. They transform together, and you have to take into account these 2 by 2 matrices where they come together. But it kind of gets redundant to work through all these examples because they end up looking, very similar here across the different functions. So hopefully you get the idea, and let me know if you have any questions, and maybe I can address them in a future video.